So calculus 2 recitation session 3, and the topics will be relative growth rate and the L Hopital rule. So let's just give the definition of the theorem of the L Hopital rule. So I be an interval containing a point A, and we suppose that function f and g are differentiable, and derivative of g is not equals to 0 for all x in the interval, except possibly at A. Then we suppose that one of the following holds. The limit of the function f of x as x approaches A is equals to the limit of the function g of x as x approaches A is equals to 0, or the limit of f of x as x approaches A is equals to the limit of g of x as x approaches A equals to plus or minus infinity. Then, the limit of the quotient f of x over g of x as x approaches A is equals to the limit of the derivative of f over the derivative of g prime of g as x approaches A, provided the limits on the right-hand side exist or is equals to plus or minus infinity. Let's know of importance that this rule will remain valid for one-sided limit also, as x approaches A either from the left or from the right, or if A is replaced by plus or minus infinity. We apply the rule as many times as needed, as long as we still have an indeterminate form. And the indeterminate form, it's the one written there, 0 over 0 or infinity over infinity. So let's just start the recitation with question number 1, which involves relative growth rate. So this one, we start by reading in flat-land, rate at which jobs are created is proportional to the number of people who already have jobs. If there are 15 million jobs at t equals to 0 and 15.1 million jobs after 3 months later, how many will there be in 2 years? So there's a derivation, and we can start by the high school formation population, the rate at which jobs, so let's call this one p prime of t, the rate at which jobs are created is proportional. It's proportional to the number of people who already have jobs. So that's how we start. Then, if we want to remove the constant of proportionality, this symbol there, this is the same as p prime of t is equals to a constant of proportionality multiplied by p of t. Then we do separation of variables. We have derivative of p with respect to t is equals to constant multiplied by p of t. And then with that, we can separate the variables equals to k multiplied by t of t. And then we perform an integration. So this one will become ln of p, that's the integral on the left-hand side, is equals to k multiplied by t plus a constant c. Then if we introduce exponential on both sides, we'll be having exponential ln of p equals to exponential kt plus a constant c. Then exponential of ln of p is just p. So p equals to exponential kt plus c. And using the rules of indices on the right-hand side, we have that this is still equals to, this implies that p equals to exponential kt multiplied by exponential power c. Observe that exponential power c is just a constant, so we can say that this is the same as p of t equals to exponential kt, then you multiply by, let me call the constant p of naught to be the initial population. So the arrangement is of this equation is p of t equals to p naught exponential to the power kt, where k is now the constant or the relative growth rate in our formation. Now, in the question, we have that 15 million jobs at t equals to 0. That should be the initial population. And we have 15.1 million jobs 3 months later. So we can call PT as 15.1 equals to 15, the initial population, exponential 3 months later, that is 3 divided by 12, that is 1/4, and then K for the rate, because we are finding the rate. So if finding the rate here, we first divide 15.1 divided by 15 equals to exponential power now K divided by 4. And then again, we introduce natural logarithm, which will become natural logarithm of 15.1 divided by 15 is equals to natural log of exponential K/4. And this part here becomes K/4, because if you use the properties of natural log, we have natural log of E equals to 1. So this is natural log on the left-hand side, 15.1 divided by 15. So we solve X. K, sorry. So K becomes 4 natural log of 15.1 divided by 15. So the relative growth rate is approximately 0.0266. And that means we can write our original equation, which is this one. I'm putting in oval shaped, that P of t equals to the initial one, 15, exponential. We have now the relative growth rate, 0.0266, and then multiplied by t. So if we have the value of t, we can solve this question. For our case, t equals to 2. So that means P of 2 for the years, equals to 15 million exponential to the power of 0.0266 multiplied by 2. And the population here will be approximately 15. After you solve it, 15.8196 million. Evaluate the integral. So this integral, it's an integral of 1/1 plus 49x squared, which is the same as integral 0√3 divided by 7 dx. 49 is 7 squared, so it's 7x squared. So if we let u to be equals to 7x, this will mean that derivative of u will be equals to 7 with respect to x. And now we can change the limits of integration using this one, u equals 7x. So to have the integral, the first one, u equals to 7 times 0, the first limit of integration, the lower limit. Another one is u equals to 7 times the x is 3 radical 3 over 7, which is just radical 3. And now from du equals 7 dx, here we can have that the denominator is 1 plus u squared. And then if we isolate dx, we have du over 7. So we can have 1 over 7 out of the integral sign. I'm having du. So the integral here, it's a special one, because the integral of 1/1 plus u squared, it's arctan of u. And then using the fundamental theorem of calculus, we have the limits of integration from 0 to radical 3. So we have 1 over 7 out of the parentheses. Then we substitute the upper limit for u, that's arctan 3 minus arctan 0. So the answer becomes 1 over 7 arctan of √3. For number 3, again, the integral here, so we can rearrange this one to be t squared divided by square root of 1 minus t power 3 and then squared with respect to t. And then we let u, the choices of u, as I said in class, are mostly one in the square root sign. So, but the one in the parentheses for the square root sign is t cubed. So u equals to t cubed. So derivative of u will be equals to 3t squared with dt. Now, we have the integral. Whatever is in the denominator is square root of 1 minus u squared. And now let's check t squared dt. We have t squared dt here. So that means if I was to isolate t squared dt, I'll get du over 3. So 1 over 3, it's there. And I will have du. And this integral, again, it's integral 1 over 3. The integral of 1 over u squared, it's arc sine. Arc sine u. In this case, you say plus constant c because it's indefinite integral. It doesn't have limits of integration. So we have a third arc sine, and the u was t cubed plus a constant c. Let's do number 4. We apply L Hopital's rule, just using the definition that we had before, and we have different kinds of indeterminate form. In this case, if I was to do an inspection, which is not graded, is if I was to factor out infinity for the x, I will have infinity multiplied by sine 3 pi divided by a very big number. It's sine of 3 pi over a big number is 0, and sine of 0 is just 0. So it's an indeterminate form of the type infinity times 0. So we have to perform an algebraic manipulation to have it in the form, we can say 0 over 0, or the one that I used for L Hopital's rule, infinity over infinity. So let's rearrange this to have limit as x approaches infinity, and we rearrange to have this 3 pi over x, and then don't change the working, the question, but rearrange it, have 1 over x here. So that's the same as the way it was before. I'm only having x as 1 over x in the denominator. So this now it agrees to the form of 0 over 0. So it's that form. So I can use L Hopital's rule. So I'll draw a long arrow and I'll say L Hopital's rule. That means differentiate the numerator first, and the derivative of the numerator, it's just cosine 3 pi divided by x. Then don't forget to multiply by the derivative of the argument, which becomes minus 3 over x squared. That's a chain rule. Let me use parentheses. Then you divide that by the derivative of the denominator, which is minus 1 over x squared. Again, if you inspect this, before you inspect, you can simplify, and you can cancel the negative signs and the x's. So that by simplifying, you have limit as x approaches infinity of 3, because x's are canceling and minus is canceling, you get 3 cosine of 3 pi divided by x as the argument. And then you inspect by substituting infinity for the place of x, and you get that 3 pi divided by a very big number is just a 0, and cosine of approaches a 0, and cosine of 0 is just 1. So this one becomes limit, this one becomes 3 times 1, which is 3. That's the answer. Finally, for this recitation, we find the limit as x approaches 0 of this function, of an exponential function. So this is a type of the form 1 minus 0, that's 1, and then 1 of divided by small by 0, as x approaches 0, you get one this type. So what we do, we introduce natural log by setting, we can say let y to be equals to 1 minus 9x to the power of 1 over x. So if we introduce natural logarithm, we have natural log of y equals to natural log of 1 minus 9x to the power of 1 over x. And by the properties, we'll be having natural log of y equals to 1 over x, natural log of 1 minus 9x. So this is the same as natural log of 1 minus 9x divided by x. That is the natural log of y. So finding the limit as x approaches 0 of the y now, because y is 1 over 1 minus 9x to the power of 1 over x, it's the same as limit as x approaches 0. Don't forget, if I was to introduce exponential ln of y, I haven't changed anything, it's still y, which is equals to the limit as x approaches 0 of exponential ln of y, which is ln of 1 minus 9x, all this divided by x. By the limit operations, so be having that this is the same as exponential, then the limit first, as x approaches 0 of ln of 1 minus 9x divided by x. And if you check the exponent part, if you substitute 0, you get ln of 1, which is just a 0, and then divided by 0. So again, in the determinate form of 0 over 0. So what you do, you differentiate. Now here use L'Hopital's rule, and a long arrow, and I'm writing L'Hopital's rule. So you have exponential power limit as x approaches 0. The derivative of the numerator 1 minus 9x is just minus 9 divided by 1 minus 9x. That's the derivative of ln of 1 minus 9x. And then the derivative of x is 1. So dividing by 1. So in short, this is the answer in the numerator, in the exponent there. And then you substitute x with 0. You have exponential minus 9 over 1, which is just minus 9. And this is the answer. That marks the end of recitation 3.